It gives me insane, tremendous pleasure to introduce a legend, a real legend. Dr. Professor Hartwig Kunzel is here from Germany, and what makes him special, he's one of the only 2 Germans I know that has a wicked sense of humor. Hartwig runs the Department of Hygrothermics and with the Fraunhofer Institute. He is the inventor, developer, father, godfather of WUFI, and he has looked at buildings all over the world. He's going to give us the opening session on 70 years of Hartwig's knowledge. And this is amazing for a 35-year-old.
Yeah, that's amazing.
So please welcome Professor Dr. Kunzel.
Okay. Okay. Well, yeah, thank you very much. I'm really honored to have been invited to give the first talk today. And I'm even more honored to see that apparently nobody slept in. Everybody's there. So that's a great opportunity for me to talk about building science, about the lessons we've learned from our field test site, and this would be the main thing. Joe said that I have a sense of humor. I hope he will still say that after this. So there was a time when Joe was bragging about his Porsche. His Porsche was bigger than anybody else's. Except for Andre Desjardins, maybe. So now I show you what I have in my garage. I think this is the biggest Porsche you probably have ever seen, but it's not mine. I've seen it in an art gallery in Australia, in Hobart, and where all these kangaroos are from. And actually hunting these kangaroos with my camera showed what happened to my car at that time. I don't know whether you can see that if you go down these gravel roads. But apart from that, I must say, Tasmania is a really great place. So if you haven't any travel plans yet, it's a good time to go there when it's winter over there, because no people are there, just kangaroos. And this picture I've chosen to show you that we can also have fun in Bavaria. No? Pretty much the same as you have here at the summer camp. And this was in 2005, but we've been there before, also 2001, and so on. And Achilles, he's not here yet, tried to open the barrel or the keg of beer, which was a bit of a problem. And of course, we all went to the Oktoberfest in Munich. Probably many of you know that. There's a lot of fun too. And why I am showing that is that at that time, Americans came to our field test site and they destroyed the German myth of building perfection. And I will explain you later on how that came about and what the differences in constructions may have to do with that. Then before we get in too much celebration and so on, there was also some hard times. Oktoberfest was canceled for 2 years. Also summer camp was canceled. And now I think it's the right time to go right into our field test site. This was when we set up these different test huts. It was necessary after World War II. Building materials were scarce, new building materials were developed, and walls became much thinner than before. They had a better load-bearing capacity, so one thought one could have it thinner, and this also caused problems. When you look at the picture, you probably see that building science is quite different from rocket science. I mean, Joe always talked about that, and he must know. He lives in both worlds, or lived in both worlds at least. So what's the difference? If you take research, rocket science or other stuff, you usually do it because it's driven by an interest. You want to do something with it. If you develop a rocket, you will either want to impress your neighbor or hit upon him. Yeah? If you are a building scientist, what are you doing? Nobody is interested in what you're doing. Nobody else. Building scientist? Okay. So what do you do? Well, difficult to explain. Actually, what we're doing is we're solving problems, everyday problems. And that's also important. You know? Maybe even more important than rocket science for many people. So I will talk about the problems and how we solved them in the beginning when that field test site was inaugurated. And Joe is right, 70 years. I didn't follow all that, of course, but my father did. That's him. Taking here, he has a temperature sensor because he measures the surface temperature of interior walls. Why does he do it? Because with these thinner walls, we have more problems with condensation, followed by mold growth. So that was a real problem. And they had to find out whether it has, what was the reason for it? Was it the building materials or not? And therefore, we set up these different test huts. All of them, each of these test huts is made out of a different building material. Some had thicker walls, some had thinner walls. And what was also important was the climate. In the 50s and the 60s, we had very cold winters. So the climate, we installed a meteorological station, which was very, I would say, simple in the beginning. Just on top of the roof, there was a temperature sensor and a sensor for the solar radiation. Looked a bit better in the 60s, in the middle, but you can see that there's a lot of snow there, so it was really cold at that time, different from now. And on the right-hand side, you see our meteorological station now. So if you have a field test site, it's very important that you document not only what you're measuring, but also what the weather data are, because you have to relate one to the other. Now, this shows you, and I don't want to go into detail, what we covered from 51 to 2001, so 50 years when we had our first celebration of having this field test site for 50 years. And, well, stucco, coating, cladding, from the beginning until now was always a feature. Flat roofs was always important because they tended to leak much more than sloped roofs and things like that. Retrofit heritage conservation became important. Thermal comfort became increasingly important. But you could say in the beginning, the main issue was moisture. Moisture as condensation from the inside, leading to mold growth, but moisture also from the outside due to wind-driven rain. How did we solve that problem? Well, we just heated our buildings more, installed central heating systems, and controlled the temperature by opening the windows when it was getting too hot inside. Is that a good solution? Well, for moisture it is. If you overheat and overventilate, you can be sure that your building will stay dry. Unless you're living in the tropics and you overcool and overventilate, then this is a different story. How do I know? Because people from these countries start buying WUFI. So they must have problems. Yeah, but then, of course, it couldn't go on like that. We had the oil crisis in the 70s, so energy became more expensive, and everybody said, well, now what we need to do is we need to save energy. We need to insulate. Yeah? So we did a lot of investigations on that, only to come back to moisture problems. The more you insulate, the more energy efficient you are, the less energy is there to dry out the moisture. And that's the reason why we had to work with the problem of moisture again. And so it was not solved once forever. We had to re-tackle it again. So now, what did we do? Field tests are a quite interesting thing. You can learn a lot, but they're also expensive. And therefore, you also do lab tests. They are not as safe as field tests. You don't know exactly whether you get the same results. But when you do computer simulations, that's cheap, and you get the same results, at least as long as you have validated the model with your field tests. So that's possible. A big advantage of computer simulations is also that the field test results, all that knowledge you have, is just valid for that location or for that climate zone. If you go to a different climate zone, things might be completely different. And that's also important to note. There is no building where I can say one size fits all. You can build it almost everywhere. There might be some, but they are not very common. Now, in the 60s, people started to think about solar energy. Why don't we use solar energy for our buildings? Isn't that much better than heating? So we had very large windows, large glazing systems, and did all those tests here. Also the question, how do people feel inside when you have such a large glazing system? Is that still comfortable? In winter, not really, because the sun getting in dazzles you, so you have to put down the blinds. In summertime, building overheats. So this is what we learned very fast. In wintertime, you have even more heat losses because the heat losses outweigh the solar heat gains, at least in the climate zone as we have it in Germany, and I'm quite sure the same holds for Massachusetts. And also, if you have more daylight, you usually have less comfort, not only because of thermal comfort of overheating, it's also, if it's too bright outside, you always have to adapt. Yeah? You always have to put down the blinds, put them up again, then you have to put them down, then it gets too windy and they go up automatically. In real drama, I'm sitting in such an office and I regret it. Yeah? I thought, when you're in Germany and you're looking to the Alps and have a nice view, and I really enjoy that, that's great, but they're in the south. So your window is facing south, and that can get very hot, and also when the blinds go up, you just have to leave. You cannot stay in the office anymore. So I think this is what we learned, that it was maybe not such a good idea to have these very large glazing systems, but architects love them, and they still do it. Now, there's another thing about that. If you have such a glazed facade, no building, we did some tests because we figured out, we saw that the facade heats up when the sun shines on it, and that could be used for heating the building. So if that air goes up there and then you open the window, catch it, maybe take a window that tilts at the bottom to the outside, then you will get all that warm air inside. Good idea. Maybe in wintertime, not in summertime. And people open the windows more often in summertime than in wintertime, and then it gets increasingly hot. And then you can use as many shading systems as you like. It's still getting hot. And this is what we've seen here, and we did measurements of that temperature in that thermal boundary layer of air right in front of the facade. This is the air that you get when you open the windows, or when you have a decentralized ventilation system, it just sucks in that hot air. And on average, that's 6K, so 6 degrees Celsius warmer than the outside air, so the air in front of the facade. On average, monthly mean temperature average can be much more, because during the night there's not much difference. And this is a real problem. This is quite often overlooked. When I talk about this, people say, well, never thought about this. I thought if I have a good shading system, that's enough. Not when you open the window, not when you have a decentralized ventilation system. Next story. I've shown this before. We have here 2 twin houses. Not quite sure, it was 2014, maybe 10 years ago, where we can do, first of all, we can, of course, validate any models or simulations that we have, but we can also directly compare 2 systems, either 2 HVAC systems and measure the energy consumption, or we can compare different insulation systems and so on. And that was done. It was a company that had produced reflective roof insulation, so reflective insulation. And they wanted to compare that to mineral fiber insulation, and mineral fiber insulation was about 20 centimeters, so a lot of insulation. And the other one, that the reflective film insulation, was maybe 2 to 3 centimeters. So we said, oh, possible. If you want to do it, if you pay for it, we do it, but we're sure that it wouldn't work. Your system, this is just crap. Can't work. Yeah? We've tested that before in the garden top plate and so on. We said, no. Well, we tested it. And because we really wanted to prove them that they're wrong, we did everything. We measured everything possible. We measured heat flux, we measured temperatures, temperature profiles, everything. We measured, of course, we have our meteorological station there. And then we compared that. And we measured the energy consumption for heating of that attic. And this is what we got. This was a pretty windy winter time. And you see here for 1 day, but we also did this for several months. If you look at the energy consumption there, it's higher with the mineral wool, with the glass fiber roof, than with the reflective film insulation. How is that possible? We wanted to prove them wrong, and now we got these results. Of course, we discussed this with the manufacturers of mineral wool, and they immediately gave us another project, and we measured that again, and we improved the air tightness, did blower tests, and everything sealed. I mean, this attic was sealed in a way that nobody will ever do that again. Yeah? And now it's okay again. Reflective film insulation shows a higher energy consumption than that with the mineral fibers or the glass fiber insulation. And I thought, okay, everything is good. But I had some doubts when I heard, yeah, you can seal everything and you can do blower tests. Yeah? And then you can go below 0.5 or even lower than that. But still, what about wind washing? And I looked at all these results again and figured out, okay, they didn't only seal it better from the inside with a blower test, they also sealed everything very carefully from the outside. Even took a higher density fiberglass on top, just to avoid that wind washing effect. And we have more results like that, but it's very obvious that when the wind washing was stopped, and that was the most important part. So the major energy hog was not that it was not completely airtight everywhere. It was more the wind washing effect of the fibrous insulation. And I think this is quite important to note, because this is something you cannot measure when you do a blower door test. You don't realize that. A blower door test may show you that from the inside, everything is perfectly airtight. But from the outside, you still have that wind washing effect, and that can be a large energy loss, especially when you have a windy season. And I think this is something we have to tackle in future more, because I know that people are talking about it, but there are no ideal solutions yet, at least not for every roof assembly. Now, another thing that was quite important was heritage preservation and how to retrofit buildings. We have a lot of very nice Tudor houses or half-timbered houses, whatever you want to call them, in Germany, and they were all plastered or rendered over them on the outside. And then people said, well, this is stupid. They looked so beautiful in the past, and now we have done this, so we took it off again. And then applied interior insulation. We had a lot of damage due to that. So we had to find a better solution for that. We did quite a few investigations too. And we figured out that driving rain is a big problem there. Also, the airtightness is a problem. It's not easy to get such a construction durably airtight. Why is that? First, we figured out the whole structure moves much more than masonry buildings. And we just have experience with masonry buildings in Germany, lately also with some timber structures. But even these timber structures don't move as much as such a Tudor house, when it's windy, when the seasons are changing, and so on. And therefore, we did quite a few investigations with companies together to find a solution of sealing the joints between the filling and the stud work. And sometimes it worked for 1 year, sometimes for 2 or 3 years, but then it failed. So this is not a long-lasting possibility. It's not like a car. No? A car is more rigid. There you can do it. You can seal that for several years, not with such a wall. And therefore, the Tudor houses fail in regions where you have high driving rain loads. And either there aren't any, or they have special constructions, like something you see here. This is from Switzerland, where they actually had additional roofs to protect the facade. No? Quite interesting. So that works. This house is pretty old. All those, let's say, attempts to make the whole thing really airtight and watertight from the outside failed. Now, driving rain was one feature that we investigated all the time since we have our field test site. Because architects, I don't know, but I should say architects, or let's say engineers, also in building science maybe, keep forgetting that driving rain was always a serious issue, and in the past we took care of that, and now we have no roof overhangs anymore because we think we are capable technically to solve all the problems. And sometimes it works, sometimes it doesn't. So we had here in the 60s already such a test hall. We reconstructed it in the 90s again. This is in the middle. And we have these wall elements that you can take out and you can weigh them so you know what the water content is. They're oriented to the west, where we get all our winter and rain from, and also to the east, where we also have a roof shelter and hardly any winter and rain from the east. So the water you find in the east is condensation. The water in the west is condensation and moisture from winter and rain that was absorbed or penetrated. Yeah? So you can see immediately what's happening. And we see here the differences on the left-hand side with the brick wall. The water content profile in such a masonry wall, 38 centimeters thick. This is not unusual for a massive wall. And on the north side, it's completely dry. The west side, there's quite a bit of moisture in it. But then it stops somewhere in the middle because there is a mortar joint between two vices of that masonry. And on the right-hand side, you see the water content at the orientation west and east. In the beginning, they always have some construction moisture, and then it dries out. And of course, it dries much better on the east side than it does on the west side. And on the west side, you see some dry better, some don't really dry at all. And when the moisture content goes up, you can see at the same time on the bottom that this was due to a winter and rain event. Now, with brick, this was still more or less okay. And then we introduced new building materials, which are insulating by themselves, like autoclave-rated concrete, and did these tests again, first without any stucco, then with stucco on it, and then they got wetter and wetter. That was much worse than when we had a brick wall. And in the last few years, I learned in Vietnam, they had the same problem. They have concrete buildings made of concrete frame, and then they fill in masonry. That's the normal standard construction. And they used to use clay bricks, fired clay bricks, as they call it. But figured out that there are two problems associated with that. First of all, you need a lot of energy to fire the bricks. And secondly, the clay, the loam that you need, you take from the rice fields. And that's a problem. Yeah? They grow mostly rice, and then you need, for rice, you need stagnant water. So if you take away the clay, you will also lose the water. Yeah? So they are looking for alternatives, and then some companies from Europe came over and said, well, take autoclave-rated concrete, much better. No problem. But they still applied the same stuccos that they mixed on site and got a lot of damage. Yeah? They said, why? It's the autoclave-rated concrete. It's not as good as brick. Yeah? Yeah, to a certain extent, but you could do something about it. You could introduce a stucco that doesn't absorb that much water and doesn't hand it on to the autoclave-rated concrete masonry. And this is something we already learned in Germany quite a while ago. My father did a lot of these investigations. So if you have very low water-absorbing stuccos and coatings, but they should still be vapor permeable, then that works quite well. And when you do this, then you keep your walls dry and damage-free. You know? I'm quite surprised that in Germany, we have it now standard. Everybody knows it, or should at least know it. In other countries, even in Europe, many people haven't even heard of that. No? Yes?
Howard, why is the AAC more vulnerable? It's got more air space, right?
It's got more air space, and the problem is that it absorbs moisture readily, but when it's drying, it can only dry or mostly dry by vapor diffusion, whereas brick has very fine pores and can also dry by capillary action again in the other direction. That's the main difference. Yeah? It's the drying. Okay, thank you for your question. So this was another thing which I think is important, and we also simulated that and really found out that if you have the right specs for your stucco, then that works in most climates quite well. Then rainwater penetration. Yeah, we knew about that. You see this on the left-hand side. When on exterior insulation systems, you call them eaves, we call them external wall insulation systems. You put tiles on that, then you get frost damage after a while. And the reason is that in the mortar joints, between the tiles and the mortar joints, sooner or later you get cracks. And even if the mortar joint is water repellent, in that crack water will go in, and then it takes very long to dry out, and when you have frost, then it all comes down. Left-hand side took about 12 years. Right-hand side was a bit faster. And interesting enough, it's mostly at the bottom where it starts. So you would expect the highest wind-driven rain load is on top. But if you have tiles like that, the water is just running down. Yeah? So most of the water is at the bottom, and there it also dries more slowly than on top because there's less wind. And that's the reason why it starts at the bottom. And now this is why I said, well, we can still learn something from the I already knew it because when I first came to the United States and we were talking about cavity walls and insulation and things like that, and we were only used to masonry cavity walls, and we did really a lot of field investigations where we proved that it doesn't really matter whether you ventilate it or not. You can fill the whole cavity with insulation, which is a good idea, and it doesn't change anything of the behavior of the wall. And then I think it was John Straub who said, yeah, he heard this too, but it just doesn't work here in the United States. And see, what does it mean? It doesn't work. Yeah, if you don't ventilate, and you get problems, especially in summertime. So we did simulations and we figured out, yeah, it's true. But it's only a problem when you have a timber structure on the inside, and if you have a masonry structure that just absorbs that water vapor or that solar vapor drive and then dries out again in wintertime. It's not a problem, but so it depends on the construction you have. And the same is true for the example here. This was one of the houses I showed you before with these roof attic tests, insulated roof tests. And when the American experts came for the Oktoberfest and the WUFI course, we also showed them our field test site, and they looked at the window details and said, well, this window must be leaking. I said, are you kidding? There's no problem. Do you see any damage? No, they couldn't see any damage, but they were sure that it was leaking. Okay, when they were gone, I became curious. I thought maybe they're right, as John Straub was right before. And we took samples. And what you see at one house, well, we couldn't see anything, but we had here moisture contents of 10 volume%, which is a lot. And the other house, there was not only high moisture content, there was also, everything was brown because ants were creeping up there. For them, it's an ideal condition. It's warm and it's humid. They love that. Why was there no damage? Yeah, because masonry is not that easily damaged by water. But it doesn't mean it's good. And once we started to do timber constructions, we had the same problems as we had here. And this was a lesson we had to learn. And I think the Stowe company introduced that first in Germany, that you need drainage or something like that, because they had to pay a high price here in the United States with all the condominium problems and so on. So you see, it all comes down to the way you're building, to the way the moisture susceptibility of the construction. And if you have a more moisture susceptible construction, then you need to take more care. You need to know what you're doing. You need more building science knowledge than when you have masonry. So you could say, well, keep on building with masonry. That's maybe not the best idea. We'll see that later, because the carbon footprint is much higher. Until now, we could say, well, it has a higher carbon footprint, but it lasts centuries, and your timber structures are rotting away within 50 years. But that's not true anymore. And therefore, the carbon footprint stays. And I think the rotting is solved. Okay, just a short summary of what I just said. And I think this was interesting to see, because coming from Germany, you think everything is perfect. Well, it used to be like that. Now, when you take the German trains, you know it's not the case anymore. Yeah. But here, we've seen that this was not true, even not at that time. We have another problem. Well, some people might like it, red, gray, black or green. It depends on what's growing there. The question is, why does it grow? Why didn't we have this problem before? So some people figured out, and that's correct, it has to do with the clean air. So Holzkirchen is very close to the Alps, so it has very clean air. So why with the clean air? Because sulfur dioxide in the air actually prevents that microbial growth. So acid rain is good actually for helping against that pest, that soiling. And it's never dirt, it's always some kind of microbes. And we figured out what kind it was. So algae are usually green. When they're getting dry, there are some that turn red. Like maple leaves, you have green ones, you have red ones, so they're pretty much the same. So they have two possibilities, and that gray or black stuff is all kind of fungus. Different kinds of fungi there, but most of them are black because they have to protect themselves against the UV light, much like humans do. So now we knew that. The question is, where does it grow? Southeast, almost nothing. North, something. West was the worst. But that's also depends on the location. So we did a lot of tests there, measured the surface temperature, and looked at the different samples of external insulation systems. The biggest problem was, and we will see this afterwards, when you had two neighbors. One retrofitted their building, and the others did not. Just painted over it. And you waited 5, 6, 7 years. The retrofitted building really looked ugly, dirty, like we've seen before. And the other one did not. So how come? We'll see this afterwards. We did also thermographs, and you see already there's a difference because we had different kinds of paint coats. Now we also figured out that all these microorganisms don't grow at the same rate all year long. It takes some time until it starts, and then every fall it goes up and then stays stable again. So apparently, fall is a problem. But why? Well, it's more humid in fall. You get more often condensation on the exterior surface. So we measured the frequency of exterior condensation on such a insulated wall. That was pretty high, much higher than the frequency of driving rain. However, we had 10 times more water coming from driving rain than from exterior condensation. So the question is, what kind of solutions can we find here? Now, the problem is when you have anchors like here for your insulation system, then these are small thermal bridges. And therefore, that surface over that thermal bridge stays a little bit warmer than the other parts of that surface. So they stay white, and the rest becomes black. If we hadn't this problem, you would maybe not see that. You could say, well, that's on purpose. But here you can't. That's another big problem. Now, the challenge was, what can we do so that somebody who retrofits, or if people retrofit their buildings, that it doesn't look more ugly than if they don't do it? And we figured out, well, it had to do with the insulation. If you have only little insulation, you see this here on the bottom figure, then the temperature usually stays above the dew point of the ambient air. If you have a lot of insulation, it always falls below, and then you get condensation. And once you get condensation, well, then you get also microbial growth. We did more tests. We figured out, we also wanted to simulate that to find out where does this happen. We realized, for instance, when you're close to a lake, this happens more often than when you're somewhere up in the mountains and things like that. So it had a lot to do with the dew point of the air in the microclimate that you were in. So if you have more insulation, you have more surface overcooling, There is one remedy for that. That is when you use low E coating, that will reduce that overcoating because you have less emission, infrared emission to the sky in the night. And with the simulation, you can identify the risk, the risky constructions, and also the risky microclimates. Yeah? You don't need such a paint coat for all climates. In the inner city, there's usually not a problem. Because there's not so much radiation to the sky, you have smog and everything, so that shelters the surface. And every time you have a problem that is really a nuisance, then there are some inventions. And one invention was here the lotus paint, lotus effect. And that was really something, and I hope it works now. This is a lotus leaf, and I did an experiment with that. I just poured some water on it, and you see what happens. Can't get any water in it. It just jumps out again. Isn't that amazing? What a fantastic effect. Yeah? So, and the company also thought that was really a great thing. And why is that? Because they have, as you see on the left-hand side, they have this textured surface where water just cannot go in, it just runs over it. And almost with no friction, as you've seen here. Quite interesting. Now we did tests. Comparing this lotus paints to other paints. I call it here nanostructure paint because we were not supposed to call it lotus paint, because that was a brand name, therefore, but you know what it is. And you see, well, after a driving rain event, we went outside and we took samples. It's like a blotting paper that we take, or cloth, we weigh before, we put it on the surface and afterwards, and then we know how much surface water, or how much water was clinging to the surface. And this is what you see here. And you see the silicate paint does quite well, but this is also because it has a higher water absorption, so it absorbs some of that water before you are able to do your measurements. So, really good thing. Then,
how important is it that the surface stay clean and free of debris?
No, that's pretty important. And the question is whether that will be the case with such a product. That's not easy because the plant itself repairs it all the time. Yeah. And here, that's a good question. Yeah. But it's actually not such a good idea as we thought because, I don't know what you see here. We did the same thing after a very cold, clear night. And then you get, in the morning, you get condensation, and it's interesting that the amount of condensation that you're measuring is rising in the morning. So we always thought, what's the reason for that? The reason is pretty easy. You have a rise in dew point in the morning when you're in the countryside. So why is that? It's because the sun, there's a lot of water also on the grass and everywhere, and that evaporates, and so you have a short peak in the morning of the dew point, and then of course you get more condensation. But what's more interesting here is that the lotus paint, nanostructure paint, had now much more water clinging to its surface than all the others. How can you explain that? We thought water would just run off. Yes, water does, liquid water, but not vapor. Yeah? Vapor creeps in between these spikes and then forms water there. Yeah? So it's not the best solution because wind-driven rain is a problem sometimes, but that condensation is mostly more of a problem. Yeah?
So it works well for bulk water, but not vapor.
That's it. That's it. And I think we would never have found out without just a field test. Yeah? When I first saw this, it hit me. I didn't expect that. Yeah? It's not something that you would expect. And we also wanted to prove, because we were appointed by the company, that this is a good thing. And we had to tell them, well, it works well against wind-driven rain, but with exterior condensation, it's not a big deal. Yeah? Might be the opposite. So these are the lessons learned here. And what I haven't said yet, well, the silicate paint had the best performance because it absorbed some of the water. So it absorbed the condensate. But the wind and rain, this is, as we've seen before, shorter, but much more water. And then it's not absorbed, it will drain. So this is maybe a good solution to, yeah, let's say to get a grip of both of these effects. So now I think I have to hurry a little bit. Green roofs are also very popular at the moment in Germany. And what you see here is we wanted to know how much water is on the membrane beneath the green substrate, the substrate with the green plants, and what that would mean for the construction. That was the major issue here. And we also saw that we have chemicals in the membranes that can do this, be beneath such a substrate with green plants. And those can be washed off, and it can also be a problem. So green roofs are not always that green. That was the first finding. Lessons learned. It was interesting that green roofs may be colder than cool roofs because, first of all, the plants reflect quite a bit of the near-infrared light, about 60%. So they are very effective, like cool colors. Secondly, they're shading the ground. And thirdly, because water will be absorbed during rain events, and then that evaporates again, so you have an evaporative cooling effect. This is good for thermal comfort. It's not very good for many timber roof assemblies because they stay pretty cold on the outside, and so some people have probably already heard that if you have a cool roof in the wrong climate, this is not a good idea. And a green roof is about the same thing, might even be worse. In Germany, we don't have so much timber construction anymore. We have concrete structures quite often as roofs, and then we put insulation above them. That works quite well when you have a conventional roof, here with XPS. With a green roof, you see this moisture uptake over the years. So the XPS insulation, we always took samples, we probed that roof, so you see that it's going up. And the assumption was, when we did this calculation, that we had 100%, and we could confirm this with a field test because we always had dew point and dew point temperature and surface temperature were exactly the same. So you had 100% RH there. And then you see what's happening over the years. And the company that wanted us to do the test said, no, this can't be. This must be leveling off, your simulations are wrong. So we took probes again after 19 years, and they showed that no, our simulations are right. Yeah? There is a problem. Yeah? And after a while, there's so much water in it that the thermal resistance also goes down. Yeah? When you do the same thing with EPS, so one is extruded polystyrene, that's XPS, and this is expanded polystyrene, EPS. They get so heavy, 50 volume% of water, and it's very expensive. Or we didn't dispose of them yet, because when you do this, they charge you by weight. Yeah? And the weight is all water. Yeah? So we waited for it to dry out, but it just doesn't happen. It seems to stay there eternally, I have the feeling. Okay, lessons learned from that. when such a foam insulation is in contact with water at the warm side, that results in moisture accumulation. If it cannot dry out sufficiently on the other side, the cold side. And the speed of accumulation depends on the temperature gradients. Therefore, when you have a thicker insulation layer, the temperature gradient is less. If it's thinner, you have the same temperature difference over less thickness, so the temperature gradient is higher. So having more insulation helps, and also the vapor permeability of the material, as we've seen. XPS does much better than EPS. Now, we've seen this gets wet, and of course, that comes with an energy penalty. What about fiberglass insulation when you got water in there? And I think Hedlin and others did some laboratory tests there and figured out that you can increase your thermal conductivity 2 to 3-fold when you have water in there. We did the test here, and you see the roof. So we wanted to be sure that we have a real vapor barrier at the bottom. That's aluminum foil. And we have that roofing membrane on top, which is also pretty vapor tight. But the company or the manufacturer was convinced that because the roof gets so hot, that water will dry out by vapor convection. We'll see afterwards what's happening. We also tried to figure out and did also simulations of that, what the roof temperature actually was. And when you had a very dark roof, as we see here, you got here, this was in September, sometimes it's even higher in August and July, 60 degrees, we measured up to 80 degrees surface temperature. That's pretty high. And if I figure out at 80 degrees what your vapor pressure is, then it's pretty high and you would get vapor convection. Yeah? So this was quite reasonable to assume. Of course, it wouldn't work with a cool roof. And here you see this was painted white. During the night, the roof surface temperature is always much lower than the ambient air temperature, but during daytime, it's with a dark roof much higher, with a cool roof a little bit higher, but on average, the cool roof has sometimes even a lower temperature than the ambient air, yeah, on the daily average. That's quite interesting to note. This, I said already that if you have very bright, very white colors or green, then you can have a problem with the drying potential. Now, we simulated something that happens in practice quite often. You're about to close the roof and it's raining, thunderstorm. So what do? Manufacturer said, nothing. Get afterwards, due to that high temperature, you get your vapor convection and it will disappear within a couple of weeks. It's gone. Okay. We tested it. Inspected it after 3 years, the water was still there. It wasn't that much water. It was less than 2 liters per square meter. So, wrong theory, but why? What happens? Of course, at 80 degrees, you get a pretty high vapor pressure. We analyzed the whole thing again. We figured out, we can actually calculate the surface temperature very well. During daytime, nighttime, that works. So we were sure that works well. Then we compared our simulations with the measurements in summertime and in wintertime. And here we measured the temperature and the relative humidity just beneath the roofing membrane. And you see here, and now you see the problem. Every time the temperature goes up, the relative humidity goes down. That means the water is just disappearing. Yeah? It always goes to the coldest side, and this within a couple of, not even hours. Yeah? So you don't get these high vapor pressures. Yeah? So that was the wrong thing in the theory. In wintertime, of course, but there it doesn't dry. You have a very high relative humidity on top. And it's always 100%. All the water's up there. And you can also see how we simulated this surface temperature quite well. There are, on the right-hand side, some spikes in the measurements, in the simulation that you don't see in the measurement, and that is due to snow on the roof. Yeah? So that's still difficult to figure out when you have snow and to consider that or account for that in your simulation. So this is what we can say now. The maximum vapor pressure is controlled by the lowest temperature in the assembly, yeah? Not by the highest, yeah? Even if there's water in it. Again, we looked at the different positions. Exterior was just beneath the roofing membrane, somewhere in the middle, and in the interior, and it just shows the same thing. In summertime, most of the water is at the bottom on the vapor barrier, and then it moves up in wintertime, and most water is on the top, and therefore you see these fluctuations here, daily fluctuations, so vapor is actually moving back and forth. And if you have that, then this is a latent heat effect that can be quite important. This is what Hedlin said. But now we did the simulation. We did the whole thing, and with the simulation, that's good. You can either account for the latent heat effect, or you say it's zero, the heat of evaporation, which is not realistic, but just to see what the difference will be. And we figured out, and you see here the hourly values, these spikes, and then you see daily means. Or in this case, it was even running monthly averages, and you see that there is not that much difference, because the energy you're losing during the night, you're gaining back during daytime. Water cannot really escape, so it's going up and down. So what you lose in the night, you gain in the day. And on average, it cancels out. It doesn't make a difference. It only makes a difference when you have a real shift in water from one side to the other. You know? And that's actually the case, and I don't know where you can see it, but you see that in springtime, there's a bigger difference between those two curves, calculated with and without latent heat, and in fall. These are the seasons when the water is actually moving. There's a net movement in one direction or in the other. So, is that important in fall and spring? No, not that much. Because in wintertime, you don't have that. During the heating period and during the cooling period, when you have peak temperatures, insulation is dry, more or less. Yeah? Therefore, you could say, it's maybe not such a big deal. Yeah?
Is that relative to the climate zone?
Could be. I mean, it's climate zones like ours, and also yours here, is pretty much the same thing. I think as long as you have a climate that's so stable that water stays on one side, mostly, there's not a problem. No? If everything would move, but even then, it's not twofold or something like that. It's just a little difference. No? I think we overestimated the problem. No? It's not really there, and we did this calculation because we cannot show the field tests we've done. Company didn't like it. It was a foam company, not fiberglass company.
What about Phoenix? So, like, we have places in the U.S. that are uninhabitable.
Yeah.
But people live there anyway.
Okay, well.
Kind of like this building?
As I said, if you want to know more, I mean, you can only do a simulation or do a field test there. That would be a good idea. Then. But we can discuss this later in more detail. So it just summarizes what I just said. And the lessons learned is that what I also said, that we have overestimated that effect in the past, and moisture accumulation from insulation may be a bigger problem, you know? Especially because most people think, well, this insulation material is not susceptible to moisture at all. It doesn't have a problem. Yeah, but it can get wet. And if it gets wet, then the thermal resistance goes down. Yeah? You lose more energy. Okay, now, that's my favorite. And I have to hurry up a bit. Performance of bio-based building materials. Yeah, we know. Sometimes you find mold, as you can see here on bamboo, on straw, less on reed, less on cattail. Agriculture materials seem to be more resistant. That's true when you harvest them in winter, because then there's no sugars in anything, no nutrients anymore in the stems. That can help. But what's the whole hack about it? Why do we push these bio-based building materials? At least the European Commission does, and I think for your government as well. And yeah, one reason is because we did a good job in the past with the energy of operation. It came down, and we even produced energy. So yeah, if you have a durable building, that's a good thing. Now, the embodied energy, we didn't count before. We start now. So we look at the carbon footprint. That's an advantage for renewable materials and also for all the bio-based materials, because they sequester carbon dioxide when they're growing. And once you build them in a building, and the building is durable, should last, then that carbon will be stored for 50, 100, 200 years or more. That's a good thing. Yeah? Sometimes there are also problems. The real challenge is if you don't know exactly what compounds you have in here if you want to do recycling. Yeah? And we find that many fire retardants and so on are actually not that good for your health. So what do? Well, we just replace them with other fire retardants where we don't know yet whether they are good for your health or not. Yeah? But once you deconstruct your building, you don't actually know what's in there. This is changing now, because now you need to register everything. This is a very bureaucratic way of dealing with that, so you know exactly what's in there, at least for the moment. And another problem is disposal. Yeah? Materials with fire retardants, as I said, and treated timber are often toxic waste. That's also a problem. Yeah? So it all comes down to saying, no, we don't want any end of life. We want to reuse the building. We want to try to not even recycle it. We reuse it as it is. It should be as durable as possible. Then this would be the best solution. Yeah? But then it means that there are no rotting and nothing other. There are some things that are good about these bio-based materials. Because they're hygroscopic, they tend to dampen moisture peaks. As you can see here, these are measurements that we've done in these roofs here. One was with mineral fiber insulation, and the other one with cellulose fiber insulation. And you have here the daily mean and the daily min and max, and you see of the relative humidity that you measured either, as you can see here, on the top of the roof or the bottom of the roof, yeah, in the assembly.
I'll do a sound check when I get up there.
So, and it shows you, okay, that's quite an interesting effect. Yeah? It helps to avoid moisture peaks if you have a hygroscopic insulation material. So now, these are interesting things, interesting investigations we did. Straw. Straw is cheap. Farmers produce a lot of that. So why not just take it as insulation material for a wall? The company did this, we did the test, And because straw is so natural and so good, and I don't know what, I should not take any cementitious stucco, so because that's bad. Let's take clay stucco and lime stucco. So this is what we tried here. And that was our west side, so where we have the driving rain from, or get the driving rain from. After the first heavy rain, the clay stucco came down. Yeah? And we had to replace it by timber cladding. Yeah? One stucco was still there. The lime stucco, sorry. Then we probed the whole thing again, and we looked at the one under the cladding and the probe that we had in the laboratory, and there the mass content, moisture content was about 10% by mass. That's not too much. That's reasonable. The other wall that was still existing with the lime stucco, well, had quite a bit more on top, 20%. Well, maybe not that bad. But then over 20%, up to 30%, that's probably not a very good idea with straw. So we could say, no, that's not good enough, and this is not enough protection for straw bale. But there was another problem. Even without being exposed, there were already a lot of microorganisms in there, yeah? As you can see here. And that's a big problem because there's mold and other stuff, and it just stays there, right from the beginning. And when you now compare the susceptibility to microbial growth, especially mold growth, of straw with untreated, it's untreated soils fill, you see, when it's red, this is not good. Yeah? So you see that you need not that much. The humidity must be pretty high in order to get mold growth on untreated cellulose fill. But with straw, wow, that starts 20 degrees above 75% RH. So the question was, is it the same for all, or the clay, or the clay stucco and the lime stucco? And I said, well, the clay stucco we don't really know because it disappeared within a very short period of time. Yeah? And then it was protected well by the timber cladding.
Ready?
Yeah? But as we also had it in the sample that was not exposed, that means there is a lot of stuff in there when it just comes from the field. Yeah?
But they took all
So
our presentations yesterday.
my feeling is that we'll discuss this later. You need to treat that before. You cannot just take that straw bale and from the field and put it into your wall. Yeah? There are too many microorganisms in there. That's not healthy. Yeah? So I think that's the biggest problem. We'll come to that. Another thing is, and that was also interesting, there was a company and they thought because everybody now wants bio-based materials and they just produced exterior insulation systems, or eaves, with rock wool. They said, no, this is not good. Now, well, there are wood fiber boards, but the competitor already does it, so we take hemp fiber boards. So what they did here, and they have learned their lesson, they knew that you have to seal everything very carefully around the window and so on. And so I think on first sight, this was well done. At first sight. This happened after a couple of years. Look at this quickly, and you will see here, these are mushrooms. These are mushrooms. Where do they come from? Well, they have been there before. Yeah? The spores have been there before. The same problem with straw. Yeah? There is too much stuff in there already that can hurt the whole construction afterwards. I'm not supposed to show you that, and therefore I go over it. But I think it's important to note this. And for me, the lessons that I've learned from that is bio-based non-timber materials may be more susceptible to moisture than the materials that we already know, wood or wood-based products. Yeah? Why that is, I don't know exactly. I guess it also has to do with the lifetime of these plants. A tree will be around for a couple of hundred years, many centuries. A hemp plant is just a year or so, or two. Yeah? Bamboo is 20 years. It's much less, so they don't need that much protection against all these microorganisms. That could be one explanation. And I also think in order to avoid a strong initial moisture content, if you have a timber product and you do wood fiber, well, there are many processes in between until you get the wood fiber board, where it's heated up, where it's washed and things like that. And when you just take hemp from the field or straw, then this is not the case. And you need to disinfect this material prior to installation, either by heating it up or by doing something else. But something must be done. And the last thing is that I think only experts in timber construction should attempt to use other bio-based materials because they know already how to do it right. Yeah? They might still fail. But others who do it because they think, well, there's already so much competition with wood fibers, I take something else. It also sounds good. Yeah? We have legalized marijuana in Germany now, more or less, so there will be more hemp fibers in the future. Yeah? So, actually a good idea, but not a very sustainable one.
Are there any bio-based products that you have found work better than the others?
Better than anything based on timber? No. Yeah, maybe these from the materials from aquaculture, like reed, like cattail, and things like that. They could be comparable. Yeah? And the others, maybe the problem is that they were not disinfected. Maybe it's different when they are clean to begin with. Yeah? But we don't know.
I think most of us here who have dealt with mold and moisture and buildings are suspicious of the idea that you could disinfect something entirely. So what I'm wondering is, have you had a chance to try disinfection of these materials and then test it to see if that theory works? I just doubt that
We didn't.
they can be that clean.
This explanation I just got from a manufacturer when I said, well, this is a big problem. Yeah, you need to, we have a different straw, we have treated it, we've done, and so on. Yeah? But I think, I just wanted to show the problem, and I think there's no real solution yet. With wood fibers, it works quite well. The percentage of wood fibers for exterior insulation systems in Germany is pretty high, 15%. Yeah? So it's, and most of that because EPS was reduced, not mineral fiber. I think that's quite interesting. And that seems to work if you don't really, if you do it the right way. But with the other materials, I think we still have to see whether that will work or not. And after what I've seen here, I'm cautious.
I used to build straw bale houses 35 years ago in the high desert of Colorado. And I was taught by like the best guys, blah, blah, blah. Anyway, we were admonished to never, ever, ever build a straw bale house in a moist environment. It has to only be built in arid climates.
Yeah. That makes absolutely sense. Build straw bale walls only in very dry climates. John.
So I heard the same thing, except I was told you should only build straw bale in dry places, and you can build dry places in most places. You would use like a 4 or 5 foot overhang around a single story house, walk around the porch or something like that. So it became not quite as dry as Colorado, but became dry enough. And we did field test studies that looked almost identical to yours, and we didn't have the problems with the clay falling off. But that's because we...
Did you use clay?
Yeah.
Ah, okay.
Clay and lime stucco, those are the two side by side. The clay did better, et cetera. But it was all because we had at least a little bit of an overhang. But at the bottom of the wall, because we only had a 12-inch overhang, that's where we had problems in both walls. But those walls were, 10 years later, when we demolished the test hut, they were still doing pretty good.
Okay. Yeah, that's interesting. And I think, well, you said you had a roof overhang. This, our test hall doesn't have a roof.
A lot of places, what was said,
Roof overhang at all, and I'm quite sure you wouldn't find the same problem when you're on the other side, so east side where there's hardly any rain. Yeah, so it's a rain problem here. Yeah, you also saw it here. It was the problem with the mushrooms was below the windowsill again. Yeah, and therefore I'm saying if somebody wants to tackle that, they should have experience with timber structures. Now, well, I'm getting right to the end. I think I could show that field tests can be important. They serve as ultimate benchmark for building energy and hygrothermal model development and validation. Also for dynamic HVAC performance evaluation. I have not shown you that here, but this is also something we have seen when we compared heat pumps with gas heating systems and so on in the beginning in the 80s, 90s, and now has changed a lot. We can also design laboratory tests and validate that, because a field test takes quite long, and if you want to know whether a certain material has the characteristics or assembly has the characteristics you need, you can also do a laboratory test, but the laboratory test must make sense. So if you do a climate simulation, it should not have a climate that's much more severe than what you actually experience. Yeah? So that's also something where this can be validated by a field test, or should be validated by field tests. And as I see it, field tests are the only method to investigate property changes due to aging and degradation, because that takes time. And you don't know exactly what process will be there, and then you find out. I think that's quite important. Also, application limits can be explored with that, because something that works well in one climate does maybe not so well in another, especially when you have severe indoor conditions. Canteens or something like that, swimming pools might change a lot. And also the impact and consequences of installation flaws, of usual wear and tear, to see what is actually happening there in reality. We can always assume 1% of the water goes behind the first line of defense. Yeah, we can assume, but do we know? Somebody has a better heating system, doesn't do it. So this is something you can only test in the field at the real building assembly, and it's also pretty difficult to test it in the laboratory. They also help to demonstrate the performance of innovative solutions, as they have seen. And they also help you detect and understand unexpected phenomena. That, for instance, lotus effect is good against wind-driven rain, but not against surface condensation. And it also raises, of course, new research questions, because if the results are different from what you expect, then you have to carry on doing research of that. So with that, I'd like to finish by first of all saying, for me it was a wonderful time here, and has been before. I did presentations 2002, 2003, 9, 15, and 24, so it's now 5 times. We always had a lot of fun, as you can see here in the pictures below. And I would like to thank Betsy and Joe. They have been wonderful hosts. And also you see Christine, daughter of Joe, has a nice dog in her hand, and that's a Dachshund. And the Dachshund is the mascot of Munich. Yeah? You might not know. Okay, so I'll show you that. So that's the Munich Dachshund. It has a hat and also lederhosen. In this bag, I brought a Bavarian Brack for Betsy and Joe, containing wheat beer, white sausages, and that famous Bavarian sweet mustard. Okay. Okay.
Thank you, Professor Dr. Kunzel, and especially for the mustard.
Well, welcome.
I'd like to say that we are up to our first break, so see you all in 30 minutes, and let's get rolling again.